Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 1st, 2026, just 1 week ago. It reveals a startling disconnect and mixture of experts models, showing that attempts to enforce expert diversity actually backfire, increasing weight overlap by up to 114% while failing to reduce activation overlap at all. The paper is titled, Geometric Regularization in Mixture of Experts, the Disconnect Between Weights and Activations. And as we'll see in the analysis, these findings challenge the standard geometric intuitions used to train sparse neural networks. Table 1 provides the hard numbers backing up that claim about regularization failure. If you look at the first row, the baseline model naturally reaches a tiny weight mean squared overlap, roughly 5 times 10 to the negative 4, meaning the experts are already distinct without any extra help. However, the next 2 rows reveal the surprise. As we introduce and strengthen the orthogonality penalty, the overlap doesn't drop. It actually jumps up by 39% and then a massive 114%. This confirms that the regularization isn't just ineffective, it actively degrades the natural geometry of the weights. So, while Table 1 showed the geometric failure, Table 2 reveals the cost in actual performance. The baseline model achieves a validation perplexity of 5.94 with a tight error margin. But when we apply the orthogonality constraint, the score worsens to 6.00, representing a 0.9% degradation. Crucially, look at the variance term after the plus-minus sign. It quadruples from 0.08 to 0.32, which indicates that the regularization destabilizes the training process. Alright, Figure 1 plots this weight activation gap explicitly. The solid blue line tracks weight overlap, and you can see it shooting upward as we increase the penalty on the x-axis, confirming that the weights are becoming less orthogonal. In stark contrast, the dashed red line for activation overlap stays strictly bounded within that pink horizontal band, regardless of the regularization strength. The stats box in the corner confirms this disconnect, reporting no significant correlation between how the weights look and how the experts actually behave. Well, Table 3 breaks down those gap metrics numerically across the full regularization sweep. If you scan the activation MSO column, notice how remarkably stable it is. The values hover tightly around 0.57, regardless of how hard we penalize the weights. Meanwhile, because the weight MSO actually increases with stronger regularization, the ratio between them shrinks from over 1,000 times to about 200 times. This proves that even drastic changes in weight geometry fail to make a meaningful dent in the functional overlap of the experts. Okay, having seen the gap metrics, Table 4 now presents the final performance impact across 3 different datasets. The first row shows Wikitext 103, where the method manages a marginal 0.9% improvement. In contrast, the middle row confirms the degradation on tiny stories, with performance worsening by the same amount. Finally, the PTB results at the bottom look promising with a 7% drop, but the huge standard deviation indicated by the asterisk warns that the training is too unstable to rely on. Wrapping up, the core message is clear. Weight space orthogonality is a broken lever for controlling expert diversity. Since static weights simply do not predict dynamic behavior, future optimization strategies must pivot to regulating activations directly, rather than forcing geometric constraints that the model ignores. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.